Yeah, let's get started with today's session. So, uh, during the first session, we were discussing, I think there were some queries around, how we can do load forecasting or deal with time series modeling in MATLAB. So, in today's session, we will go through that. In the first part, we will mostly talk about how we can kind of pre-process the data, right? Once that is done, we will look at two types of modeling. One would be with neural networks, and the other one would be with like time series models like AR models, ARMA models, MA models, all those kind of things. So before we get started, I think there are two people. Yeah. Before we get started, just wanted to understand how many of you have already, you know, either studied or worked on any form of time series modeling, just to understand like uh, uh, like what you have done so far. Has anyone worked with time series modeling or say ARMA or MA model or time series forecasting in using neural networks? Those kind of things. Have any of you done previously? You can just let me know by typing yes or no in the chat. Please. Okay. So Shivam mentions no. Okay, so most of you have are new to time series modeling. Cool. In that case, we will go through some of the examples. So whenever we are talking about time series modeling, we are essentially talking about uh, some kind of forecasting into the future, okay, by based on previous data, okay. So that can be done by using some kind of mathematical models, okay. So since machine learning is used for more like predicting some kind of classes or predicting some kind of continuous values, there are particular models which can be used specifically for sequential data or data which is varying with time. Okay, so whenever we are given, so let's take examples for these kind of time series modeling. So one of the most common examples would be to predict the weather of a particular place. So let's say you have weather record for maybe tens of years or hundreds of years, and you want to predict the weather condition in the upcoming month, something like that. So weather conditions are kind of repetitive, right? Because throughout summer you will notice a particular type of temperature, right? It usually remains high. Sometimes there will be high humidity in air also. On the other hand, during winters, it would be extremely dry. You will not experience rainfall. So every winter will have similar kind of trends. Every summer will have similar kind of trends. And based on that past data, I will be able to predict what will be the temperature at a particular place in this day of this month, right? So this is about forecasting or using time series data which varies with time, to forecast what will happen in the future. Okay. So today we will look at we will look at a particular example which is around load forecasting. Okay. So what is load forecasting? When we talk about load forecasting, it is about predicting how much load will be consumed by a particular load center at a certain time period. Okay. Now there is again some kind of trend there, right? Because when it's summer, the consumption of electricity kind of goes up because the temperature is high. So you turn on ACs or coolers or fans and whatnot. Uh, and every summer will kind of have that same kind of load consumption, or a particular month in summer will show similar trends. On the other hand, on winters you will see less consumption of electricity because the fans are not turned on or ACs are not. So whenever you are presented with these kind of data, what's the first thing that you should do? Okay. Can anybody answer that to me? So let's say you are told, you are given some past data around, load forecasting. Okay, this particular center is consuming this much amount of electric load. You are presented with that data in some Excel sheet or something, right? So what's the first thing that you do is my question. Does anybody have any answer? Okay, Ripunjay mentions clean the data. Okay. Any other responses? So cleaning the data is one response that I got. But any other suggestions on what we should do when we are presented with the data? Right. So yeah, Ripunjay, you are right. The first thing which we should do is rather prepare the data. Right. Cleaning is a part of it, and there are other ways to prepare the data before we feed it to some kind of mathematical model. Right. So that is what we will do in the first part of today's session. We will try to prepare the data first. Okay. So I will open up this script for load forecasting underscore NM. Okay. So let me just run this and try to explain you what this means. Okay. Okay. Are the fonts big enough in the live script? Yes or no again in the chat. It's just for everyone to be able to see what's really going on. If the font is small, you will not be able to understand it. But is a small big enough visually for the text that you are seeing? Yes, no? So let's try to understand what this data means, right? You are presented with this data. It's called NYISO, and it basically contains dates or time and the load consumption, preferably in maybe like kilowatts. What's the load consumption at individual load centers, or like let's say a particular region in the New York City, right? So these are different regions in the New York City, which are kind of the name of the place is kind of shortened, but say western part of New York or northern part of New York, things like that. So at 12 in midnight, what was the load consumption at this region called capital, or at Dunwood, or north or west, right? So similarly, uh, what's the load consumption at say 5 in the morning or 10 a.m. or 1:26 in the afternoon, things like that. Okay, so this is the raw data that I have. Now I need to prepare the data. Right? It might contain some missing data, it might contain some noisy data. So I need to make sure that my data is in a proper state before I feed it to some machine learning model or some mathematical model. We'll see. So now you have all this information, and we can do multiple things here. For example, if I want to say take one column, say this capital column, and want to typecast all its values as string, I can use this string command. Okay. Like if I want to treat these things as text, so what I have to do is pass the column name, like the name of the table dot column name, and if I just pass like use the string command, this gets converted to a string. Previously, it was just a double or a number. Right? So these kind of operations are possible. Okay, when you want to kind of change everything in a column to a certain variable. Okay, so the first thing which I want to do is something which was mentioned in the chat, is I want to clean the data. Okay. Why do I want to clean the data? I want to clean the data because there are certain missing entries in the data. Okay. And if I have missing entries, this might not lead to good predictions, because remember, I am using this data to train some kind of model. Okay. So if I want to do that, I might want to fill missing entries. Okay. So this particular task I can access from this task drop down here. Okay. Say there is a separate section for pre-processing data, where you can clean missing data, clean outlier data, smoothen out data, do things like that. So here I want to clean the data, and I want to rename this table. So initially this table was called NYISO, if you notice here, right? Now I want to call it NYISO missing. Like I'm renaming it kind of by replacing the missing data with new entries, thereby cleaning the data. Okay. So I have cleaned the data. Good. It might take some time to do that, because if you notice here, there are around 1 lakh data points, right? So what did we? Yeah, I think there is some echo. Yeah. So initially we had the raw data. Now we just cleaned out the missing points and added new data to it. Okay. Next part would be dealing with outliers. Okay. Does anyone know what an outlier is? Can anyone mention that in the chat? We come across this term outlier sometimes when we are talking about machine learning and whatnot. But does anybody know what an outlier actually is? Can you mention that in the chat? Say out of bound of interest. Okay. Okay. Anybody else? Any other response? Just like from looking at the term outlier. So something which, if I have to break it down into simple explanation, so something which lies outside, right? That would be an outlier. Yeah, points that are different from the rest of the data. Right. Good response. So exactly. So if something lies outside or a bit far away from the main set of points in a data set, that is called outlier. Okay. Outliers are like exceptional points, and they do not contribute to the overall trend of the data set, right? So it's a good idea to clean out those outlier points as well. Okay. So here, let's take something like maybe Dunwood. I just want to clear the outlier for maybe one of the load centers, say Dunwood. And I can choose the cleaning method also. Like, do we want to remove outliers or do we want to fill outliers? If we want to fill outliers, what kind of interpolation method we would use, things like that. How do we even define outliers, right? Because outliers would be defined by certain thresholds. What would that threshold be? So we can define that as well. So once that is done, once we have decided that, so we come across this thing. Okay. Now in this plot, you can kind of see that the cross points are like a bit spiky, right? But on the other hand, these kind of contribute to outliers because they are clearly outside this black boundary. And this black boundary is something which we have defined as outlier thresholds. So anything beyond this outlier threshold is an outlier. So what we would rather do is we would remove these points and kind of fill them with points which are lying inside this particular boundary. Okay. And there are multiple methods to do this. Linear interpolation is what we are using. Okay. So till now we have done two steps. First of all, we have cleaned the data to some extent. And like by cleaning, I mean cleaned out missing data points and added new data points in place of that. And what something else that we have done here is we have introduced like removed outliers, okay, and introduced new points in place of these outliers. Okay. Okay, there's a question around what is xlim ylim. Good question. So xlim and ylim basically decide the limit of these plots. So what are the limit along the x-axis that you want to show? That will be xlim. And what are the limits on the y-axis that you want to show? So if you notice here, it is slightly below 200, the lower y limit. That would be 146. Similarly, 1576 would be the upper limit along the y-axis. Does that answer your question, Kanchan? Okay, awesome. So xlim ylim is plot related, and we can define that. Let's move to smoothing of data. Okay. Now let's take another column and let's try to smooth that out. Okay. So one column in my timetable is this central column. If you notice above this column, right? And it might contain some noisy points. We might want to smooth that out. So what we can do here is we can select the input data and the specified column and choose the smoothing method. So it can be moving mean, moving median, whatnot. Moving mean is what we are choosing because that's the default. So if you notice here, yeah, okay, there are some zoom issues. Let me just fix that. Yeah. So let me try to open this figure in a new window and show you what I mean. So this is the same figure. Okay, and this is the plot. Okay, so if I enlarge this, you will notice that the light blue ones are the input data, and the deep blue one is actually the smooth data, because in the light blue one you will see a lot of oscillations, right? And this oscillation can happen due to multiple reasons. Maybe there are very subtle like variations throughout from one day to another, or there might be some uh, uh, measurement noise which is also getting introduced. But either way, we want to ensure that they do not contribute a lot to the overall trend. The overall trend is something like this. Okay? It's a bit oscillated, and we don't want a lot of these oscillations, small high frequency oscillations, to creep up in our data. So we just smooth the data out, and we end up with something like this. Okay. Okay. So what we have done again so far, we have cleaned out missing data, we have cleaned out outliers, and we have tried to smooth out the data, right? Any questions so far regarding the data pre-processing steps? If you have any questions, just let me know. Is this part making sense to you? Uh, if that is the case, you can type yes as well, just for me to understand that we are on the same page. Okay, awesome. So yeah, we have kind of dealt with dealing with data. Now we can also do multiple things. For example, we can join multiple tables. Okay. For example, let's say the the overall load condition. Let's say it also depends on weather, as I mentioned initially. So if we have a separate weather table and we have a certain load data table, can we kind of join them, right? By making sure that the sampling kind of aligns. So let's say the weather data might have different sampling. Let's say we are, kind of capturing weather data on an hourly basis, and let's say we are capturing this load data on 6-hour basis or a 12-hour basis. So in that case, we have to make sure that their sampling kind of aligns, right? They are sampled in there are no missing data when we are trying to join them. Right? So in that case, we can use this of like task called join tables. You can find it under this task drop-down. For table-based operations, there are multiple of them. If you want to retime them, synchronize them, join multiple tables, all these options are here. Okay, so we can kind of use this part and run this, and we will obtain something like this. Now, if you notice, previously we had something till west. Okay, but now we have more columns, something like KBGM, KISP, KBUF. I think these are like, temperatures across multiple places. Okay? And they are like the maximum temperature and minimum temperature at a particular place. So we have kind of combined them. If you want to use both of them for your own prediction algorithm, that is also possible. So we can go ahead with the forecasting part, but this is where we kind of like till here we have discussed how we can prepare it if the data is available to us in one of like in a timetable form or in say a matrix form, how we can smooth it out, how we can clean it out, how we can fill missing entries, all of that we can do till here. Okay. In the next part, I will kind of take you through how to do modeling using neural networks. Okay. Any question till here before we move into the next part? I'll probably yeah. Thanks for letting us know, Shubham. Any other question? Any questions anyone has? Okay, cool. Let's move on to the next part then, which is about forecasting. I'll talk about forecasting with neural networks first, and then we will look at something around different time series models. Okay. How many of you have previously heard of or used LSTMs? Can anybody let me know in the chat? Are you aware of something called LSTMs? Okay. Shubham has mentioned no. Anybody else heard of LSTMs? Yes. No. Okay. So not an issue. We will walk you through. We'll just give you a brief introduction to what an LSTM is. So LSTM, I hope most of you have heard of neural networks, right? So whenever we talk about neural networks, it can be used for multiple applications, right? We use something called convolutional neural networks for image-based applications. So let's say if you are given an image and you are told identify certain objects in the image, you can do that by using something called CNNs. But there are particular neural networks which are designed only to deal with time series data or data which kind of varies with time, because the network architecture is such that it's able to capture long-term dependencies as well as short-term dependencies within the time series, right? Because if you have a very large or rather a very long time series data, there might be certain trends which appear over a long time, and there might be certain trends which appear over a short time. And you might want to kind of capture both of them. So long short-term memory networks, okay, kind of helps you to do. Okay. So it has certain like certain functionalities to forget certain things, because you might want to forget irrelevant trends and you might want to capture like relevant trends. Okay. So LSTMs help you to do. Okay. We will not get into a lot of details on how an LSTM works today, but I will definitely share resources on how it can be used for different time series applications. And it does not always have to be from, for load forecasting. It can be used for predicting, say, like what will be the stock price for a particular company, or data which varies over time, say seismic data. So what is the possibility of this place undergoing an earthquake in the upcoming few years? So those kind of data can also be fitted to an LSTM or those kind of neural networks. So here we have this data set called smooth load data. This is what we have obtained in the previous exercise, and I have kind of saved it as a mat file. So if you want to kind of load a mat file, just use this load command, and inside it just pass the mat file name, as a string. So if I do this, or rather, let me clear everything so that I can start things from the beginning. So everything here will be kind of deleted. And it deleted everything, right? So there is nothing in the workspace now. So let's load the data first. So you have this NYISO, which is the previous data, but smoothed, right? So what we will do here is, you can train your network for multiple data. Okay. For example, if I go back and look at the data, I had multiple columns, right? So for LSTMs, what you can do is you can just take the load pattern for only one region and do the forecasting for that, or you can have the data for multiple regions and you can do load forecasting for multiple of them. Okay. So in this case, we will be doing it for multiple of them. Okay. So I am taking the load data for West region, the North region, and the Dunwood region, and saving it as this new variable called data. Okay. The first part for me would be to prepare the data. Okay. So I have the data with me now. Here, if there are certain missing points within the data, I'm using this rm missing command just to ensure that there are no missing data. Just a limit. So after this, the entire data, I am trying to divide it into two parts. Okay. First part I will use to train my model or train my LSTM network, which means I will expose the network to this train data, and during that the network will be able to kind of capture certain trends within the data which it is exposed to. Okay, so the rest of the data I will use for testing, like how well my network has performed and so on. So train part I am using for training my network, or rather exposing my network to this load data so that it is able to capture trends within the data. And I will use the test data to check whether my network can give good predictions on unseen data. Okay. So this is my motivation till. Is the division on train and test clear? Why we are trying to do that? Yes or no in the chat, please. Any questions regarding this? Why we are trying to divide the data into two parts? Any questions around this? Yeah, good. Right. So here, when we have the data, there is a way to kind of normalize the data. So what you do is you take the data, the entire training data, and you take the mean and standard deviation for both of them, and you try to normalize it. By normalizing the data, you are basically reducing the spread of the data. Okay, and that helps you to train the network better. Okay, it's just a step that we use to have good data to feed to our LSTM network. So we get the mean, and mean is mu, sigma is standard deviation. We also transform the test data by using the same mean and standard deviation. Okay. So both train data and test data are now kind of transformed. Okay. Initially we had the raw data, but we transformed it into like normalized versions of themselves. Okay. So now we need to have two things. We need to have X train and Y train. So what are we trying to predict? For a single time step, what will be the next value? Okay. So from 1 to end minus 1, that is the training like X value, and the Y value would be what I'm trying to predict. And that is basically the next step. So what I'm trying to predict is, if I know today's load consumption, whether I'm able to predict tomorrow's load consumption, something. So similarly for test, if we have today's load consumption, can we predict tomorrow's load consumption? Now, this is how, till now, we have prepared the data. We have taken the entire timetable, divided it into train and test parts, and segregated the like X value of train and Y value of train, as well as X value of test and Y value of test. Okay, based on what we are giving as input and what we are trying to predict. Okay, everything clear so far? Any questions till here? So if most of you are new to LSTMs and time series modeling, please don't worry. I'll definitely share resources at the end, which will definitely help you to kind of ramp up to these concepts, so that it's easier for you to understand what's really happening. Okay. In the next part, we will try to define the network architecture. Okay, what the network will look like. Now, if you remember here, we took 3 values, right? We are trying to predict 3 values in one go. So number of features is the number of input, that is 3. And we are also trying to predict 3 values. So what we mean by that is, if I know today's load consumption for West, North, and Dunwood regions, what would be the load consumption for tomorrow for these 3 regions is what I'm trying to predict. Okay. So output is also 3, because I'm trying to predict 3 values, and input is also 3. I'm trying to predict 3 values. Now, this thing, num hidden units, is something which is a parameter for this LSTM layer. Okay, this LSTM network. You can customize it, but more the number of hidden networks, better it will be able to capture certain nuances within your time series data. Okay, because there are certain trends which you might not be able to capture if the number of hidden units is. But again, there is no empirical rule on how many will work for a particular case. You have to decide that by experimentation. Okay, so you can change these values and see how your network performs and so on. Okay, so we define the layers. Okay, so there are 5 layers to this overall LSTM network. So the first one will be a sequence input layer, because you are passing sequence as an input to the overall network. So you need this layer. Okay. And then you need an LSTM layer, of course. How many hidden units? Num hidden units. What is num hidden units? In our case, that is 200. Right. So I am creating this LSTM layer of having hidden units 200. I can also specify the number of features, that is 3, because I'm passing 3 values in one go. There is something called dropout layer, which helps you to kind of train your network in a better way, because by dropout, you can kind of ignore certain neural connections, which is a good thing, because then you are not remembering the entire data by heart, or rather you are just trying to capture the overall trend within the data. Okay. Then you have something called a fully connected layer, and finally a regression layer. So it's a regression problem because the final values are continuous values. So you have a regression layer at the end. And fully connected is something which you also use based on the number of output responses. So you have 3 output for 3 input. You use fully connected layer at the end. Now, this is the overall network architecture that we have designed. You can also specify how you want to train the network, or what will be the learning rate and all of that stuff. And finally, you can use this train network command to train your network, right? So what are the inputs? There is an X train, there is a Y train, the architecture of the network, and the options. Okay, what will be the learning rate and what? And this train network will kind of help you to train them. Okay, everyone with me so far? Any questions till this part? So the overall workflow for training this network is kind of same for other neural networks as well. It's just that this network has a different architecture, because it is an LSTM network. So this will be something special for these kind of networks. Again, if this all of this seems a bit new to you, please, and a bit overwhelming to you as well, please don't worry. I'll definitely share resources at the end, which will help you to know more about how these networks work and how all of these commands work. So if I run this cell, this network will be trained. But since we are dealing with around 1 lakh data points, this might take some time to train. Or it might take around half an hour to kind of train the entire network. So what we will do in this case is, rather, we can use a previous version of trained network that I have already saved, and we can use it. So I'll click on this file, load LSTM network new.map, and it will load this variable called net for me, and this network is the same architecture. If you notice, it has the same architecture as the one we defined previously. Now, if we want to predict what will happen in future, we can do two things. We can predict and update state of the net. So what we first want to do is initialize the states of the network. Okay, so we use this function. It is part of the deep learning toolbox to kind of update the state of the network. And then what we will do is we will go through individual time steps and try to get the prediction based on previous values. Okay. If I run this, it will take some time. Okay, X train, I think I have not done the previous. Yeah. So let me just run all the cells. Now here we have everything. And we will be predicting the load at those three centers based on the previous values. Now, since we are going through a large number of time steps, how many time steps is that? Like it will be around 80,000 or something, or even 20,000 or something, but it might take some time since we are running a for loop. Okay. So we are predicting the y values and we are updating the state of the net. Okay. So the network state changes, the network parameter changes as we are feeding input to it, and that will help us to get better predictions as we move over time. Okay. Right. In the meantime, if you have any questions from your end regarding LSTMs or time series modeling in general, feel free to let us know in the chat. I'll just answer them on the way. Any questions, anyone? This does all of this kind of make sense to you? I know like most of you are new to LSTMs and the overall training and stuff, but that's the overall idea. I'm not talking about the overall commands, but the intuition behind why we are using this and all of that. Is that making sense to you? You can let me know through yes or no in the chat again. Okay, good. Good. Yeah, thanks for letting me know. Right. So yeah, let's kind of wait till this for loop kind of gets executed for all the time steps, because then we will be able to see certain visualizations. Okay. And again, just to reiterate, you can think of examples where you can apply these kind of modeling. Right? It can be even weather modeling. It can be stock price modeling. It can be any kind of time series data. In fact, there are even certain architectures where you can use an LSTM and a CNN together. So let's say you want to kind of uh, do certain predictions on images, right? Like on say video, because video is a time varying kind of signal. So you can also think of examples on how you can use an LSTM to do certain predictions on individual frames of a video, because that might require an LSTM and a CNN in the same network. So that is also possible. Right. So we were able to execute this. Now, if you remember, initially we had kind of used this normalization technique to kind of normalize the data. Right. Now we will do the reverse because we kind of want to compare the prediction with the raw data. So we might want to unstandardize the predictions. Okay. So we will do exactly the reverse operation of what we did while we were trying to normalize. And we will get the predictions. Okay. And we can actually plot maybe the first column, which is like, what did we take here? The west. Say we want to predict only for the west center, what is the load consumption. Okay. So here we can take the raw data and the prediction together, okay, and show them in the same plot to kind of compare them, right? So if you notice here, the predicted data is the orange one and the actual data is the blue one. So I think it does a decent job at predicting because it kind of avoids those noises, right? It is not capturing those noisy points. It is giving you a smooth kind of a prediction. And there is significant overlap, at least visually you can understand, right? From the orange predicted data and the blue actual data. Right? So visually it makes sense, like my LSTM predictions and my actual data kind of overlaps. But if you want to mathematically calculate, like how accurate this is, uh, there is this uh, value which we take into consideration called RMS error, which is like root mean square error. And if we compute this, it prints out the error for individual load centers. So this is for maybe west, this is north, this is something else. Like what is the order? Yes, west, north, and done, right? So this is the error for west, this is the error for north, this is for done. So north, I think the LSTM does a very good job because the root mean square error, which is like a measure of cumulative error, that is minimum. This one, it does decent job because even visually, if you notice, it does not take the noise into prediction, right? The noise value and actual value are kind of different. But that's a good thing, right? For Dunwood also, it does a pretty good job. So in this way, we can use an LSTM to kind of feed time series data train the LSTM using the time series data and finally, you know, get the predictions out of it. Okay. Any questions so far regarding this? Anyone? You can wait for a minute or two. Okay. I think it kind of makes sense to most of you. But we'll see how if we can share some resources around, uh, so that you get ramped up in some previous concepts to get a better understanding of an LSTM. So just to recap what we have done so far, we discussed about preparing data. If we have some kind of time series data, we might want to clean it, smooth it out, and once the data is prepared, how to kind of feed it to a neural network, something like an LSTM, right, to uh, do certain kind of time series prediction. Okay. There are other ways for time series prediction as well. For example, there are time series modeling techniques, models like AR models, ARMA models, and MA models. They, uh, they are widely used. Is anybody aware of ARMA, AR, and MA models? Have you used it previously? Can you type yes or no in the chat? Anybody heard of ARMA, MA, and AR models? Okay. I guess most of you are new to ARMA and you know MA and AR models, but don't worry. So the idea behind ARMA, AR, and MA models are that they are we will get to see what they mean in a short while. But they were mostly used for applications in econometrics. Okay, some kind of econometric model, some kind of stock prediction, and those kind of applications they were widely used. But regardless of that, they can be used in any kind of uh, you know any kind of models for any kind of time series modeling for that. So the the way to go about modeling this in a simple way would be to use a certain type of app. So under this apps tab, you will find apps from different domains, right? Cockpit optimization and whatnot. If you want to explore more apps, just click on this drop down and they will kind of show up. The app that we are planning to use in this case will be econometric modeler. Okay. Now the name might sound a bit unusual because we are trying to do load forecasting, but we are using an econometric modeler. This is because uh, regardless of the data, this app can be used for different types of time series modeling. So let's take a look at how this, like what is the interface and how we can kind of load data and fit modules. Okay. So this is the, okay, let me check this. Let me try opening. Okay. Let me app econometric modeler app, and we can import data and then kind of start playing around with this. So before that, let me just load the data that we are using. So this is the data that we had used previously as well. Let's go to the app. So if you want to load some new data or import some new data rather, this you can click here. You can click import from workspace. So this is my workspace, and I have this timetable in the workspace. So the app gets access to all my variables in the workspace. So now let me try importing this. So when you click on this import option, this import data option will open up. If you click on this checkbox and import it, it will show you all these columns as separate time series. So now you can kind of see different types of, like you can see all the load data in a single plot. Okay, and these are like the legends for individual data points. Right? So here, what you can do is you can select a certain, say I am going with Dunwood, for example, and I want to fit a time series model to it. Okay. Now, if I click on this Dunwood, you see all these options open up. Okay. So you have AR, which is auto-regressive model. You have MA, which is moving average model. You have ARMA, which is a combination of both AR and MA, which is auto-regressive moving average model. Right. So let's just take one at a time. So let's take Dunwood, for example. And before going ahead with this modeling, we want to explore a few plots. But okay, let's just click on ARMA for now. So if you click on that, if you click on plots, or rather, if you click on that ARMA model, you will get this option. Okay, it will ask you to choose between two things. One is autoregressive order and moving average order, and you also get to see the model equation. So what's if I have chosen a zero order autoregressive and zero order moving average, then this is the relationship between the time series data and the I can say random noise, right, which is generating this data. So my time series value at a certain time instant is basically a random value plus some constant. Okay. Now let's say I increase this autoregressive order by 1. If you notice, this equation changes. Okay. Now when we say auto-regressive order, auto usually means to self. So a time sequence where the present input is only dependent on, like the present time value is only dependent on the past time value, okay, plus some error. In those cases, it is called an autoregressive model. Okay. But if I had chosen a moving average model, that is basically taking all these errors and doing some kind like present error, past error, and so on. And my present time series value will basically be a function of my present error and past error. Only that. It will not be a function of my past input, which is 5. If I also want my input to factor in, I have to increase the autoregressive order. Okay. So in that case, my present y value will depend on past y value also. Okay. So in this way, we can decide what will be the order. I can choose autoregressive order 1, 2, 3, and whatnot. Similarly, for moving average also that is possible. And they should be positive, right? Because I don't know the future value. I only know the past value. So the order is positive. Okay. Now the question here is, okay, I get some idea around, okay, this is what autoregressive model does. This is what moving average model does. But how do I understand which order to choose? Okay. So in that case, what we have to do is we have to go for plots. And there are certain plots which we can investigate. These are ACF plots and these are PACF plots. Okay. Before I proceed any further, have any of you used the autocorrelation function at some point of time in your course or in any project? Can you type yes or no? Do you know what an autocorrelation function is? Anyone? Yes, no. Okay. So autocorrelation function. So right, yeah. Thanks for letting me know. So when we say autocorrelation, it means auto usually means self, correlation kind of means similarity. So it's like how similar a time sequence is to itself if it is delayed by a certain time period. Okay. And ACF stands for autocorrelation function. PACF stands for partial autocorrelation. Again, I don't want to get into the details of it, but the idea is to find these similarities once we delay the time series by a certain value and comparing that delayed version with the original version. Okay, how similar are they? Okay, if they are similar, this means that there might be a chance that they are periodic by that certain time period, right? Because if the same features come up after a certain delay, then there is a possibility that that delay might be like a period value, right? So we can investigate that from this ACF and PACF value. Now, if you notice the PACF values, they are fairly high for 0, 1, and 2. After that, it kind of diminishes. Okay. So since till 2 I have a significantly high value, this helps me to choose the order of my AR model. Okay. So 2 might be a good candidate for the order of the AR model. Okay. If I look at moving average model, from the ACF, you see all the values are significantly high. Let's not specify anything for MA for moving average. Let's go with choosing the AR model order itself. Okay. So what I'll do is I'll again go back to where we started. Okay. So I will increase the autoregressive model to 2. Maybe not change moving average order, or maybe just increase it to 1. Okay. Now I have chosen the model order and everything. What now this model will do is try to estimate something. What will it try to estimate? So I have the model, but I don't know the model parameters. So the model will try to estimate these values, sigma 1, sigma 2, okay, theta 1 and all of this. And if you click on estimate, it will take some time to estimate, but it will show you certain results out of it. So here, if you notice, a new model has been downloaded. Okay, and it's called ARMA underscore Dunwood. Dunwood because that is the data we chose, and ARMA because that is the model we chose. And these are like the predictions and the original value. So if you want to zoom in further, okay, say here. So if you notice here, right, the blue values and the predicted values are kind of close. They are kind of overlapping, which means like it's a good fit. Okay, at least from visual inspection we kind of understand. Towards the right, you get the parameters, their estimate. Okay, we chose 2 orders for AR. These are the 2 parameters, those sigma 1 values. We chose 1 order for MA, that is the theta 1 value, if you remember. And these are other things, these are constant. If you want to get a mathematical figure around how good your fit is, these are certain measures, AIC and BIC. Generally, a high value refers to a good fit. Okay. So this modeling is fairly simple, right? Because we, at least in the LSTM case, we did not have to, I mean, the training might take some time. Here, the training might not take some time, but again, it depends on the data. So there are multiple ways for modeling time series data. This can be one method. Okay. So if you want to export what you have done, there are multiple ways to export that also. For example, let's say you automatically want to generate certain scripts. Okay. Let's say generate a live function out of this. So whatever you have done, all this code is auto-generated, and you also get the equation so that it's easier for you to understand what I'm kind of estimating. And this function gets generated. Now, if some other kind of data, like you are using some other kind of data for fitting time series model, all you need to do is apply this function on that data. Okay, and this function can be used on new data to get new predictions as well. So this is about modeling on ARMA, ARIMA, MA, and all of these things. Since I am assuming like most of you are new to this kind of workflow, so this might seem a bit overwhelming for you. But if you want to know more, I will share certain doc resources. Okay? For example, if I just type doc econometric modeler, like if I want to know more about this app and how to do these kind of modeling in general, I can rather just give me some time. Yeah, so here you have quite a bit of examples, right? Like how do you prepare time series data? How do you import time series data? How do you use vector models? All of that, and other commands that can also be used for fitting time series data. If you are new to the LSTM approach, which we tried out earlier, just go to the doc, or even from the MATLAB window itself, you can just type doc LSTM layer. And you kind of understand how you can define LSTM based networks and how that can be used for different kinds of applications. And here you like it's kind of explained also, like what is the architecture, what is it trying to do, and all of that. What's the mathematical explanation, like how do I understand the mathematics behind an LSTM layer and all of that. So here it's kind of captured. and what kind of data format I need to use and all of this. So just feel free to explore more, because these kind of modeling can be used for any kind of time series application, be it load forecasting, be it yeah, anything related to finance, anything related to seismic data, or any human activity kind of data. All those kind of things is possible. Okay. Right. So, any questions till this part before we proceed to the next?